Swayam Prabha. Digital India. Educated India.
Students, so we meet again. Once again we have a lecture on stress distribution in soils. This is the fourth in the series. We have covered 3 lectures already, and apart from seeing what is the importance of stress distribution in soil mechanics, we have also got started with the computation of stress distribution using the method of theory of elasticity. It is worth recapitulating that theory of elasticity is based on certain very basic assumptions, such as the medium is homogeneous, isotropic and elastic and a continuum. We also assume, or we ensure rather, that any typical adjacent elements in the medium, when they undergo deformation, they undergo this deformation in a compatible way. So, taking together the equilibrium equations, the relationships between strains and displacements, the stress strain elastic relationships and the compatibility conditions, we found that in all there are 15 equations and 15 unknowns, and they can be solved to get what is known as a Laplace's equation. This equation can be solved with the help of the so called Airy stress approach. The Airy stress function is a function which is a function of position. That means it is a function of the coordinates x, y, z of the medium, which means that it gives the distribution of the stresses, the overall pattern of distribution of the stresses in the medium, both with respect to x, y, the horizontal direction, and also with respect to the z direction. This stress function is a function which, when let us say suitably differentiated, will give you the stress components sigma x, sigma y and sigma z at any point at which we desire to get the stresses. That is precisely what Boussinesq had done. He evolved a stress function. The credit goes to him for evolving that stress function phi, which is applicable to a 3-dimensional problem of stress distribution subject in a medium subjected to a concentrated load on the surface. Let us take a quick look at a few slides to recapitulate all this, whatever we had discussed in the last few classes. So, in the last lecture we continued with the theory of elasticity, saw how theory of elasticity has been used by Boussinesq and how Boussinesq has evolved his own approach based on theory of elasticity, and we also saw how to use Boussinesq's approach to determine stress distribution due to 1 a point load and 2 a line load. Why did we choose a point load and a line load? A point load is the simplest form of loading one can imagine, a concentrated load at a point in a medium. See, for example, if this is the medium, at any point there can be a load. This is a point load or a concentrated load. This is known as a point load or a concentrated load. So, we have a method to determine stress at any point P or say A due to this concentrated load. In other words, if we have a number of concentrated loads and if we assume superposition to be valid, then we can find out at this point A the stress due to each one of these concentrated loads, which means in effect a line load. After all, a line load is nothing but a load consisting of a number of concentrated loads along a single line. So, if we get the solution for one concentrated load, it means that we can get the solutions for every concentrated load acting at every point along a line. And all these when summed up, or in other words when it is integrated over a finite length, we get the stress at the point A. These two are fundamental and very basic. With the help of this concentrated and line load and the method for stress distribution determination due to these two loads, we will be able to solve any problem. Suppose we have a rectangular area which has got a uniformly distributed load. Knowing the distribution due to a concentrated load or a line load, we can extrapolate it to a number of lines and cover the entire area. So, the stress distribution due to a uniformly distributed load over a large area can be calculated. If the area is circular, all that will happen is the pattern of summing up the effect, that is integrating, will change, but the basic principle, concept, the approach will still remain the same. So, once we know the stress distribution procedure for concentrated load and hence the line load, we can employ it to any area. And there are of course methods available to also tackle arbitrarily shaped areas. We shall be now proceeding further to see once again very quickly the equations and the method of computation of stresses under point loads and line loads. In this lecture, we shall quickly take a look at the calculation of stresses due to a concentrated and line load, as I said just now, and then continue with application of those to a strip load, to a rectangular area, and 3 a circular area. These, as you can see or visualize, represent 3 very typical cases in practice. Imagine, as I have said a few times in the earlier lectures as well, a long compound wall. This has got a foundation, and under this foundation there is going to be stresses induced due to the compound wall, and this can very well be taken as a small strip because it has got a very large length compared to the small dimensions in the cross sectional direction, and this can very well be considered as a strip. So, this is nothing but what is known as a strip load. On the other hand, if we have a regular foundation under a column, and if we consider the load being distributed under this foundation, then the area of this foundation, the base area of the foundation, acts as a rectangular area over which there is an uniformly distributed load, where B is the width of this foundation and L is the length of the foundation. It could be square. If it is circular of diameter say d, then again this principle can be applied and we can study the stress distribution below a circular load as well, and that is what we are going to see today. We shall be taking a strip load, extending it to a rectangular area, and then we shall also see how to compute stresses below a circular area. Now, a word about this superposition which I mentioned briefly. See, if we have two loads, the effect of one load and the effect of the other load can be determined separately and they can be added together to get the effect of the total load, and this is known as the principle of superposition. Let me just briefly explain why this is important and how this can be justified. Let us take the stress strain relationship for the soil below the foundation. Let us say it is linear, and in fact if you look deep into the method that we have used, you will find that we have assumed the elastic properties E and nu to be constants, which means that this modulus E is a constant, or it implies that the stress strain relationship is linear, sigma E relationship is linear. Now, if this is linear, then this theory of elasticity that we have used is called generally as linear elasticity theory. Now, when we employ this theory of linear elasticity, then and only then the principle of superposition is valid. Imagine we are applying a load or and a corresponding stress, say, which we can call as P1. This stress P1 is going to produce a strain, let us say, that is E epsilon 1. Now, suppose I apply an additional stress of delta P, that is going to produce an additional strain, say delta epsilon. This means that the total stress applied is P1 plus delta P, say P2, and the total strain is epsilon 1 plus delta epsilon, say epsilon 2. Now, imagine that we are applying straight away the load P2. Then this load P2, according to the linear theory of elasticity, is going to have a strain epsilon 2, which is going to be exactly the same as this epsilon 2. This means that whether we apply P1 and then an incremental stress delta P, or whether we apply P2, the final strain remains the same. This means that the principle of superposition is valid. Rather than determining the in case we want to determine the stress due to a load P2, which consists of two components P1 and delta P, it is possible to calculate the effect of P1 separately, effect of delta P separately, and add and get exactly the same effect that P2 would have created if it had been applied directly. This is the principle of superposition, and very soon we shall see an example where this will be useful to us. Let us proceed further. Let me recapitulate, emphasize that we are dealing with an XYZ coordinate system as shown here. This is Z, this is XY, and there is an arbitrary point P and an element surrounding that in the medium. The center of this parallelepiped or the element has got coordinates x, y, z. Next, we have already seen that due to a concentrated load P, the stress sigma z at any point inside the medium is going to be given by this expression, and in this expression, if we take out P by z square, we can write the stress sigma z in terms of a factor called the influence factor, which incidentally is equal to this. Now, these three expressions are valid for a concentrated load, and therefore, for stress at any point due to a concentrated load P, the influence factor is this. Next, these are the influence factors derived by substituting different values of R upon Z in the expression for sigma z shown in the previous slide. So, a series of influence factors can be obtained for a range of R by Z varying from 0 to 2.9, and therefore, if you know in any given problem where the point at which you want the stress is lying, that means if you know the coordinates R and Z, you can calculate IF. IF multiplied by P by Z square will give you the sigma z, which we had seen in the earlier lecture. And let us take a quick look at the example which we saw last time once again. Determine the vertical stress on a horizontal plane at a depth of 12 meters due to a concentrated load 800 kilonewtons in an elastic medium. So, the solution would be find out R by Z. It so happens that if R by Z is 0, IF is 47745. This is happening because we want the stress on the surface where Z is equal to 0. Then the influence coefficient is this. Therefore, the stress sigma Z is this influence coefficient into P divided by Z square, and that is 2.653 kilonewton per meter square. Okay. Now, if we have a line load the effect of the concentrated load can be summed up over this entire length and the effect of the line load at the point in the parallelepiped can be computed. The expression for sigma z will then be this, and if we want to determine the stress due to a line load of magnitude small p equal to 400 kilonewton per meter, where small p is the intensity of loading along the line. Then for an x of 5 meters and z of 5 meters, we can compute the sigma z value as 12.73 kilonewtons per meter square. Now comes the importance of the use of sigma z computation by the principle of superposition. Take for example, two concentrated loads P1 and P2 and any point A in the medium. P1 is 400 kilonewton per meter, this is a line load actually, 400 kilonewton per meter in a direction like this, and P2 1000 kilonewton per meter, again a line load along this. So, we will compute the stress due to two line loads at a point A, which is at a distance of 10 meters horizontally from the load P1 and 5 meters horizontally from the load P2 and at a depth of 5 meters. Proceeding further, what we will do is we will compute the stress due to each load separately and apply the principle of superposition. Okay. Suppose we take the first load. The first load is P1. We know its magnitude. We know the magnitude in the sense the intensity of loading. We know the point A, its coordinates, and therefore, we can use the formula which we saw 2 slides earlier for computing sigma z due to a line load at any depth and the corresponding influence factor. We can find, if we apply that principle, that the stress due to P1 in this slide is sigma z due to P1 at the point A will be this. If I substitute the value of P1, which is 400 kilonewton per meter, and if I substitute the values of z and x, where z is 5 meters and x is 10 meters, I will find that sigma z due to P1 is 2.037 kilonewton per meter square. Take now for example, the second load. If the second load is 1000 kilonewton per meter and if the point A with respect to this load is at 5 meters horizontally and 5 meters deep, then the stress due to P2 sigma z P2 will be given by a similar formula, where now we will have the load P2 and the coordinates x and z equal to 5 and 5 respectively. This, when you substitute, you get the stress due to the second load as 31.835 kilonewton per meter square. Now, since principle of superposition is justifiable because of the approach being a linear theory of elasticity approach, we can get the total stress as the sum of these two stresses, which is equal to the stress sigma z at the point A, and that is 33.872 kilonewton per meter square. Okay. Now, we come to subject matter of today's lecture, which requires the knowledge of the previous lecture, and that is the reason why we went through recapitulating what we discussed in the last class. Now, we shall see how to compute the stress below a strip load. Let us take a look at this slide. The strip load here is defined by a width B and a very long length. The length is very large, and that is why no specific length is mentioned here. For all practical purposes, it can be taken as a infinitely long compared to B. And now, if you want the stress due to this load at point P, then we can proceed using the line load formula. Suppose this is the load, we take a cross section along the load, then this is the point P, then suppose this is the